All right. Hello. If you're just coming, I am not Chris, although we have similar last names, so I guess maybe. So again, my name is Raissa Ferron. I'm a faculty member at the University of Texas at Austin. Today, I'm going to be presenting some work done by my student Sanjita Hassan, as well. Well, she graduated, and then we still needed to finish some of the work, and my postdoc, right, who continued on some of her work. And this study is focused on surface modification of tire rubbers, and specifically we're going to be looking at some treatment processes that we did in order to try to improve the properties. So why are we looking at using tire rubber in concrete? Similar to the motivation of a lot of the work that we heard today is that we know that when we are looking at materials, we have a large consumption with materials, and when we look at a lot of materials at the end of their lives, they are not necessarily reused. When we look at tires, a majority of those are, a significant fractions are actually going to be downcycled or landfill. And landfilling in particular leads to various concerns, such as fire, because the tire is pretty flammable, and once they start to ignite, it's very hard to put them out. In addition, just based off of the morphology of these tires, that the circular tubing nature of it could lead it to catch water, and therefore that gives concerns with respect to like mosquitoes. There's been research that has shown that when you utilize tire, crumb tire, so basically ground tire, in concrete, that this can lead to improving the impact resistance. And this is kind of like where we were coming from, because this project was funded by the Texas Department of Transportation. So we was looking at this for impact resistance, particularly with respect to the application for using it in traffic barriers. There's also been work that has shown that when you start using recycled crumb rubber, that this can also improve the acoustic properties of your cementitious composites. However, when we do look at adding these crumb rubber tires into our concrete, one of the major challenges that you have is that you're going to have a significant reduction in your compressive strength. So over here you can see a figure that is just showing you that compared to a concrete or mortar sample that does not have any rubber, when you start replacing some of your natural aggregates with the rubber, you're going to have this decrease in strength. And it's going to increase as you increase your rubber content. With respect to the reason why this is occurring, one of the things to note is that when we're looking at tires, that they're going to be very hydrophobic. And this leads to essentially, it impairs the flow of your water in your mortar or in your cementitious matrix. And the result of that is that this is going to cause a local starvation at your interface where you have your rubber and your cement. And this is essentially going to lead to this insufficient hydration. So instead of having like an increase in compressive strength, you get this reduction in hydration kinetics because you're not having good bonding between your cement and your rubber. And the end result is that you're going to have a strength reduction. So one of the major ways in terms of really trying to combat this issue is to go to the source. And the source is that you have this issue with respect to the hydrophobic nature of the rubber. So in order to really look at improving the properties, we wanted to look at increasing the hydrophilicity of our rubber samples. So the goal of this work was to look at a treatment process for improving hydrophilicity of our crumb rubber cycles, crumb rubber tires, and we wanted to characterize the effect of the treatment method on the rubber, as well as evaluate the performance of our cementitious materials after we have included the rubber that has been treated. So in terms of the treatment process that we decided to use, it was inspired by work from Wu, who was doing work looking at treatment of rubber, primarily for the use of polymer composites, not cementitious composites. And in this work, it was a two-step treatment process. The first step consists of halogenation. The second step consisted of amine grafting. And the first thing that we did was really take a deep dive into this process to have a better understanding about these two different steps. Again, because his work was mainly focused on polymer composites, and he gave a generalized approach. The various chemicals that you use for the treatment process wasn't necessarily tailored to Portland cement types of mixtures. So after in-depth study and preliminary studies, Sanjita had identified two different chemicals to use. The first one is TCI in an ethyl acetate solution. And this first step here, the main goal is to try to improve the hydrophilicity of the rubber. And then the second step was mainly to graft on these amine functional groups. And primarily what we're looking at was that she selected these in order to have good bonding with our particular matrix, in this case, cement. So over here you can see our finalized process. We had our untreated rubber. We did the first step of the process. We're doing the second step of the process, and at the end you have treated rubber. And after we identified the chemicals, the key thing was to try to figure out what was going to be the major parameters for this heat treatment process, and particularly the exposure time as well as the temperature. So in order to characterize the hydrophobic or hydrophilic nature of our treated rubber, we looked at doing contact angle measurements. Essentially, the key thing that you need to know is that when your water likes your substrate better than the water likes the gas, this is going to, gas in this case is air, this is going to reduce this contact angle between your water and the substrate because your water is going to spread. So essentially what we want to do is to have an acute angle. We want to have angles less than 90 degrees because this is going to indicate that you have better wettability of the water on your rubber surface. So the first step of the treatment process, this is the TCI, the halogenation process. We looked at soaking the rubbers in the solution for different periods of time and different temperatures. The gray bars are showing you 2 hours. Oh, the cursor doesn't show on the slide, does it? Okay, I just noticed that. Okay, the gray bars is showing you 2 hours. The yellow bars is showing you 4 hours, and the pink bars is showing you 8 hours. And the key thing here is that we thought they was all pretty similar. The lowest contact angle measurement was around 85 degrees using 120 degrees at 8 hours. However, when we looked at 65 degrees at 4 hours, it was very similar. It's like two degrees different. So we decided to use 65 degrees Celsius at 4 hours just in terms of trying to optimize time as well as like energy when you start thinking about heating something at 120 degrees for an extended period of time. The second step is the amine grafting step. And in this case, we can see that, and this is done after step 1, right? So you take it after step 1, you do step 2, and we can see that the lowest contact angle measurement, and again, we want to get below 90, right? 90 degrees is like our sweet spot. We can see that it's occurring at 75 degrees Celsius for an exposure time of 2 hours. However, one of the things that we noticed is that this time period was not long enough to allow the sample to dry. So this is actually an extraneous measurement. And the best exposure time and temperature range in terms of really looking at reducing the contact angle measurement was 120 degrees at 4 hours. And again, she did a lot of work prior to doing this with different chemicals, and this was like the best combination. So the final two-step process here was looking at using 65 degrees Celsius at 4 hours for the first step, and then the second step was using 120 degrees for 4 hours. So over here, this is showing you the results of compressive strength with our control sample. So this is sample that contains only natural sand, so river sand. So these are mortar samples. And then our untreated rubber sample here at a 5% and 10% volume. I forgot you can't see what I'm doing. 5% and 10% volume. And then the light blue is showing you what happens after the first step treatment, and the darker blue one is showing you what happens after the second treated step. As I stated before, once we start introducing rubber into our composites, we get this reduction in strength, so that wasn't surprising. We do see that when we compare like our light blue, the untreated bars to like the light blue bars, after that step 1 treatment process, that we actually get this reduction in strength. So we see that even though step 1 was able to reduce the contact angle measurements, so increase hydrophilicity, that we still didn't have good bonding necessarily with the rubber and the cement, which means that we needed to do step 2, right? So when we look at step 2, which is the dark blue, we actually see that we have this increase in strength, right? So we can see that with the 2-step treatment process, when we compare the untreated and the dark blues, that we do see that we get this increase in compressive strength. We was also concerned about hydration kinetics because we are exposing these rubbers to various chemicals. And what we can see here is that when we look at hydration kinetics, that there's really no big change, right? So that is good. We did FTIR analysis to get a better understanding about what was actually happening with this treatment process. And the orange line below shows the treated samples. This is after the 2-step treatment. And the, I guess, brown line above is the untreated samples. And I'm going to point out like some key wavelengths here because they correspond to different functional groups to give you understanding about what is happening with this treatment process from like a chemical point of view. So over here, these wavelengths are corresponding to our carbon-hydrogen bonds, particularly when we go and look at rubber, what we see is that this corresponds to this hydrocarbon butadiene that is essentially this waxy coating that is on the tire rubbers, and that is something that is going to increase the hydrophobic nature of the rubber. If we compare the top line and the bottom line, we can see that absorbance peak has decreased. So that means that we have reduced that. If we look at these wavelengths over here, this is corresponding to our carbon-oxygen bonding. And this is related to zinc stearate. Zinc stearate is an activator that is used in the production of rubber. And one of the features of zinc stearate is that it does increase the hydrophobic nature. So when we look at the top and the bottom, again, we're seeing this reduction. And then this last peak over here is our sulfur-oxygen bonds. And essentially, we actually see this increase, right? So this increase is corresponding to a bond stretch that is occurring over here. And this is due to the second step of the treatment process. So this is showing you that we actually are having this grafting onto our rubber particles. We was also very interested in impact resistance results, again, because we was looking at this with the motivation for looking at using this for applications in which you're trying to increase like toughness. And we used a drop weight hammer test proposed by ACI 544. Essentially, you have a drop hammer, you have your sample, you give it a certain number of blows, and we decided to look at both initial and ultimate failure. We can see that when we look at our control versus our untreated and our treated specimens, that we get this increase in the number of drops. So that means that it takes more energy in order to bring our samples to failure, right? And then when we look at the gray bars, this is showing you the number of drops or the number of blows that it takes to go from like your first crack, so that's initial failure, to the ultimate failure. And we see that with when we compare the control to the treated samples, that once we include like rubber inside of it, we can see that we get this increase in the number of drops. So this is indicated that we get this increase in toughness. The other thing that you can see with this method is that there's a lot of variability, right? We see a lot of overlap with these error bars. So we also did statistical analysis in order to see whether this was actually statistically significant. And the end result of that is that our control samples, so the samples with no rubber and the samples containing rubbers, they are statistically different. However, when we look at the difference between treated and untreated rubber, they're essentially similar in terms of performance with respect to impact resistance. So what this means here is that the inclusion of the rubber is making a difference on impact resistance, right? However, whether it's treated or not, it doesn't really make a big difference here. That is what this is saying here. When we look at impact resistance versus compressive strength, another thing I want to point out is that we see with respect to compressive strength, as we go from light blue to dark blue, let's actually go from untreated to the dark blue, we can see that we get this increase in compressive strength, right? And this is the same whether we have 5% rubber or 10% rubber. When we look at impact resistance, as we go from our treated samples, right? So we can see when we go from untreated to, when we go from untreated to treated, we see that we don't necessarily get this increase, right? So the question here that we was thinking about is, why does the rubber improve? Why does the treatment process of the rubber improve compressive strength? Which is great, right? Because that was our goal. We wanted to increase compressive strength. But why don't we get the same effect when we look at doing our treatment process for our impact resistance, right? So why do we not see that there's a big difference once we start treating the rubber with respect to impact? And the major reason why we think this is the case is due to the differences in failure mechanisms. When you're talking about compressive strength, you're talking about a static load, so therefore our cracks tend to propagate around our ITZ. However, when we're talking about dynamic, when we're talking about an impact load, it's a dynamic load. It's a very fast crack propagation. And in this case, it may not necessarily go around the ITZ. So it's ignoring the strengthening that we have in our ITZ, interfacial transition zone. So in conclusion, we found that we were able to develop a chemical treatment process that is suitable for cementitious composite matrix. And the main goal, which was to induce hydrophilicity, was achieved. We was able to reduce this from a hydrophobic nature to one that was in a hydrophilic nature. We saw that the treatment method did not impact hydration kinetics. And we also saw that we were able to achieve our goal of enhancing the compressive strength, and we did not compromise our impact resistance. I would like to acknowledge TechStot. That was the project of the sponsors. We also have a grant from Strategic Energy Institute at UT Austin, and we also had several undergraduate students who worked with us, and they really liked doing the impact resistance tests. Thank you.